Okay, so it can be shown that eta 1, which is the total derivative of eta with respect to x minus y dash the total derivative of xi with respect to x. So we get the total derivative of eta with respect to x plus y dash the total derivative of eta with respect to y. That is the total derivative of eta with respect to x minus y dashed. The total derivative of xi with respect to x will be, keeping in mind that eta and xi are functions of x and y only. And that's y dashed. That's the total derivative of xi with respect to y. Here we are. And similarly, we have a rather long formula of eta 2 written as partial derivatives only, etc. And these are the forms, these extended forms in terms of partial derivatives is what we use when we're finding the invariance of differential equations. So now, as far as differential equations are concerned, when we are finding the one-parameter Lie groups of transformations, or equivalently in their vector field form, that leave invariant a given differential equation, then there are two conditions essentially. So we say a differential equation, let's say e of x, y dashed, y double dashed, so it's a second order ordinary differential equation. A differential equation is invariant under a one-parameter Lie group of transformations, but we will give the vector field form under the vector field xi d dx plus eta d dy. Xi and eta functions of x and y, and that's why we call these point transformations. So it's invariant under this if two things. One is that the function on the left-hand side, the function e, the differential function, is invariant. That is, if your vector field x, of course it has to be prolonged to the second order, on the e is equal to 0. So this guarantees that this function on the left-hand side, regarded as now a differential function, is invariant under this vector field. And the second condition is that this has to be satisfied along the given differential equation. So this would be along the differential equation e equal to 0. What this means is that in the process of determining the vector fields that satisfy that, we need to impose at some point the differential equation itself. Okay. And so here then there are two conditions, that this function on the left has to be invariant and it has to be along the differential equation in question. Okay, so we look at a standard second order ordinary differential equation. So we say consider y double dashed plus y minus y to the minus 3 equal to 0. So the left hand side of this function is the function e. Right. So first of all then, we have to take the second prolongation of x on the function, differential function, and put that equal to 0. Well, you recall from the last lecture what x2 was. x2 contained a whole lot of partial derivatives. So first of all, xi d dx of the bracket is 0. Then eta times d dy of the bracket, the partial d dy of this bracket is 1 plus 3y to the minus 4, then eta 1 plus times d dy dashed of the bracket. D dy dashed of the bracket partially is 0 because the bracket is independent of y dashes, and then plus eta 2, the partial derivative of the bracket with respect to y double dashed is 1, equal to 0. So this implies that we have eta 1 plus 3y to the minus 4 plus eta 2, and that's eta square bracket 2, which we need to write in terms of the partial derivatives. So eta 2 in terms of partial derivatives is eta double x, that's the partial derivative of eta twice with respect to x, and I'm just going to give the formula for this. This is 2 eta xy minus xi double x, and this is already written in a convenient form in terms of the y dashes, plus y dashed squared into eta double y, that's two derivatives of eta with respect to y, minus 2 xi xy minus y dashed cubed multiplied by xi twice differentiated partially with respect to y plus y double dashed into eta y minus 2 xi x minus 3y dashed xi y. So this thing in color is eta 2, and this is equal to 0 along the solutions of the differential equation. Okay, so that is x2 on y double dash plus y minus y to the minus 3, which is then put to equal to 0. If we're now going to put the differential equation, that means this is all going to be along the solutions of the differential equation. So we're going to put y double dashed equal to y minus 3 y to the minus 3 minus y itself. And that I will do in there. So in the next step, we rewrite the same equation, but replacing the y double dashed with y to the minus 3 minus y. And then we need to keep in mind very important aspect of eta and xi. Remember, we are solving for xi and eta. These are the components of the vector field, capital X. You have to keep in mind that xi and eta are functions of x and y only. Therefore, their partial derivatives, no matter what order, are functions of x and y only. So everything on the left hand side, the unknown functions, that is eta, xi, and their partial derivatives, are functions of xy only. They are independent of y dashes, which means we can separate after substituting for y double dashed. We can, in this equation here, separate by powers of y dashed. So we can then, for example, write down the coefficients of the y dash cubed from the left hand side, the y dash squared from the left hand side, y dashed, and separate them, and of course those that are independent of y dashed. So for example, the coefficient of y dashed cubed is xi double y from the left hand side, coming from there. There are no y dash cubes on the right hand side, and you put that equal to 0, and we do that for each of these powers of y dashed. What we end up with here is a system of partial differential equations in which we have to solve for xi and eta. So we have 4 equations. We're solving for xi and eta, which are functions of x and y. So this is usually a system of, it's an overdetermined system of partial differential equations, and they are usually linear. And we go about solving for them in step by step in a rather straightforward way. So if you're going to do this by hand, this, for example, means that the function xi is linear in y, because the second derivative with respect to y partially is equal to 0, which means xi is linear in y, which means that the integration constants may depend on the other variable, namely x. So we can say it's an integration constant times y plus another integration constant, where the integration constant depends on possibly x. And we do this step by step. We then substitute this form of xi, solve for eta, etc., and go through the whole process, which I'm not going to go into details. This can be seen eventually from the notes that I will present. What we end up in the end, about going through the whole procedure, is a specific form then of the xi's and etas. We finally get, oh dear, that xi is equal to a sine 2x, where a now is a genuine constant independent of any of the variables, minus b cos 2x plus some constant e, and the eta can be shown to be y times the same a cos 2x plus b sine 2x. So what we have are 3 arbitrary constants, capital A, B, and E. So we have an infinite vector space, but it is has a finite dimension, and the dimension of that vector space is 3, determined by these constants A, B, and E. To choose a basis, we need only choose, for example, A to be a constant, B, E equal to 0, etc. So that, for example, if we choose A equal to 1 and B and E equal to 0, we get xi is sine 2x, and we get eta is y cos 2x. If we choose B equal to 1 and the others equal to 0, we get xi is minus cos 2x, and eta is y sine 2x. And lastly, if we choose E equal to 1, we get xi is equal to 1 and eta will equal 0. So we have a 3-dimensional vector space of vector fields that leave invariant our given differential equation. So for example, one of those vector fields will be sine 2x d dx plus y cos 2x d dy. Another vector field, or what we eventually call a Lie symmetry, is minus cos 2x d dx plus y sine 2x d dy. And then lastly we have scaling in the variable x, which is d dx. Of course, the scaling in d dx also implies that the differential equation is explicitly independent of x. That's just by the way. So what we have is a 3-dimensional algebra or vector space of vector fields that leave invariant our differential equation. Just one or two algebraic properties of this vector space. We can map uniquely each of these vector fields. So if you take the general vector field xi d dx plus eta d dy in this example, we can map it uniquely to the three-dimensional vector ABE. So for example, the vector field x1 will be mapped to 1, 0, 0. The vector field x2 could be mapped to 0, 1, 0, and x3 to 0, 0, 1. And any other combination or element of this vector space can be mapped uniquely to this three-dimensional vector. Which means that the set of vector fields that live invariant this differential equation form a three-dimensional manifold. Furthermore, we can show in fact that this set of vector fields forms a group if we define an operation. The operation we will define here is the commutator or the Lie bracket. So for any two vector fields x and y, suppose we have two vector fields x and y, we define the commutator of x and y to be x operating on y minus y operating on x. We can show that this vector space of vector fields that live invariant the differential equation is closed under this operation and a whole lot of other things. And in fact, it forms a group. So therefore, the vector fields, or the set of all these vector fields, form further, in fact, via this operation, a three-parameter Lie group. It's a manifold of 3 dimensions. It's a group, and therefore, under this operation commutator, therefore it's a 3-parameter Lie group. The set also forms a Lie algebra because it satisfies the axioms of a Lie algebra, which I'm not going to express here. The next question would be, how does one use the vector fields to reduce a given differential equation? That's the next.